All right, so this formula actually was the first formula on your test. The first thing that you had to figure out in your test was to find slope for a tangent line, and you wanted to see what it went to. So there was a couple. The way WebAssign did it, it actually asked you for the slope first, not the points. On my test, I asked you for the points and then the slope. I had to break it down a little bit more. So I did notice some people's notes like WebAssign wanted these as all positive, but they were negative in this because WebAssign did that all in one step basically. So if you had done the negative, you would have noticed the next set would have come out to be positive. Basically, the exact same numbers actually. So that's where that confusion was. But most people did quite well on that. That wasn't an issue. And if you did the positive ones, but the rest of them came out to be fine, I didn't take off. I took off a point, I think, on it. That was about it. So it wasn't anything crazy. So we're going to look at what derivatives really are. So a derivative is slope. It is looking at how things change. Okay, so that's why we're going back to our slope equation. If you remember from algebra class, your slope equation was m equals y2 minus y1 over x2 minus x1. Remember, f of x is just y. So that's y2, that's y1. It's no different than what your original slope equation was way back in algebra class. The reason we write it this way is because we're going to start using it in terms of a function and not just in terms of numbers. Okay. The test that you just took, the first question had you dealing with it was just numbers. Now we're going to look at it in terms of actual equations. All right, so that's the exact same equation you just saw. The only difference is there's a limit in front of it. Because what we're looking at is we're looking at that how that bottom, they get infinitely close together to basically it becomes zero. This right here, you're going to see a ton. Okay, in a variety of forms, it's going to be X and H and A and H and a bunch of different letters in there. But that is basically the definition of a derivative. You're going to see that formula come up like 3 times in these slides. So we're basically looking at it in terms of as H goes to 0. And if you look at the slope equation, that means as the change in the point that I want gets closer and closer to 0. Now remember, I can't divide by 0. So we might have to do some manipulation and algebra to be able to simplify the problem down to be able to find what that answer actually is. All right. Let's actually use it. So let's find the equation of a tangent line for this hyperbola at that point. So very similar to what you did on your test, except we're not going to use a bunch of points to do it. We're going to use the formula to do it. So we have our limit as h goes to 0 of f of a plus h minus f of a over h. In this problem, since we're looking at 0.31, a is 3, and f of a is 1. So that's what I have. Yeah, because f of a is 1. Because remember, f of a is just y. So if you plug 3 into this problem, 3 divided by 3 is 1. All right. Everybody good with what I've set up there so far? Okay. Remember, function notation states that whatever's inside the parentheses, I can replace the x by. So that means this problem becomes 3 over 3 plus h minus 1 over h. Remember, I'm replacing that x with 3 plus h. So f of 3 plus h, remember, f of h or f of x is 3 over x. So 3 over the x becomes 3 plus h. That's what function notation allows you to do. Anything inside the parentheses replaces your x. And now we have to do a bunch of algebra. All right. So I've got a fraction over a fraction. On the top, I have a fraction minus 1. I want to make this one fraction, which means I need a common denominator. What's my common? And so we're just looking at the top now. So my common denominator is going to be 3 plus h. So I have 3 minus 1 times 3 plus h over 3 plus h. So I have 3 minus 3 plus or minus h. Which ends up being negative h over 3 plus h. Everybody understand what we did in red? Again, a lot of this is just manipulation and simplifying down through the algebra steps. All right, so now I have h goes to 0 of negative h over 3 plus h divided by h. I can put this to h over 1. We want to have it as a fraction over a fraction. So how do I do division of fractions? Yep, multiply by a reciprocal. So I have negative h over 3 plus h times 1 over h. So I can cancel out the h's, and I end up getting negative 1 over 3 plus h. Now can I plug in my 0? Yep. And I get negative 1/3. All right. So what does that tell me? That tells me that at point 3, -1, my slope is -1/3. Okay. So in all of your years learning algebra, you've only been able to find slope given 2 points. What we just did was find slope at 1 point. Okay. That is a huge deal. Yes. Well, the limit makes it possible, yes. We're going to look at ways to do it so we don't have to deal with limits afterwards. Calculus basically gives us the rules to be able to do that. So we're working towards that. So I'm doing this so you understand what we're going to do next class. But that's a big deal because up until this point, you needed 2 points to find it, and the slope could change between those 2 points. Okay, it wasn't always going to be constant between those 2 points. So when they were originally looking at this, they were looking at the path, the rotation of planets, which are not linear; they're circular or elliptical, so they change. You know how people say, "Oh, you're going to be a rocket scientist." This stuff allowed rocket science. We need to know the exact acceleration, the exact velocity of that rocket or the object at every single moment. Okay, so without this, we couldn't figure those things out. So this allowed us to start doing that stuff. So if we look at the graph here, you can see that the red is that's my hyperbola. And this blue line is my tangent line. And at that point, that's my slope. It only hits right there at that 1 point. Okay. So that gives me a tangent line, which also allows us to intercept things. Okay. So that's what we're looking for. That's what makes this concept and using limits to do it so powerful. Okay. All right. Look at this one. So velocity, when you're given your function is telling me the position of the object. Okay. Velocity is telling me how fast that position is changing. In your car, that would be your speed. Okay. So your speed is telling me how fast your car's position is changing. Since we're looking at how fast something is changing, or position is changing, that is slope. That is what we're looking at. That's our derivative that we're talking about. Okay. So we can use the slope or the limit formula that I found to find what's known as instantaneous velocity. We're going to find the speed of that object at any given moment. All right, so the first thing you're going to need is I highly doubt anybody in physics class? What is the what's the equation of motion? All right, it's 4.9 times t squared. It's meters per second.
So is that why for every single question back on the final in algebra, like to read it out, I use always 4.9?
Yes. Yeah. Because you see it a lot. All right. So the first question we want to find is what's the velocity of the ball after 5 seconds? Is that my velocity equation? No, that's my position. That's telling me where the ball is located. My velocity, I've got to do my limit form, the slope, or that instantaneous velocity formula that I just looked at. So I've got to do the limit as h goes to 0. You're going to hate this equation after a while because we're going to use it a ton. And then after I show you the next thing, we're not going to use it anymore. And you're going to go, why did I have to learn it? It's so you understand. That's in the end, it's really just so you understand what's going on. If I just jumped from this to here's a derivative, most people wouldn't have made the connection to where it was with the slope. And that's a really, really important thing to make sure you understand. All right, so we're looking at it in terms of 5 seconds. So A in this case is going to be 5. For those of you who plugged in 5, what's f of 5 going to be? Since most of you probably did that immediately just to see what the answer was going to be. What's the answer? What was it? Well, yeah, it's close to 125. 122.5 seconds, because that's f of 5. So that we need that number. So I have the limit as h goes to 0 of 4.9 times 5 plus h squared minus 122.5 over h. We don't know what h is. H is the limit. It goes to 0. All right, so simplify that out. So if you simplify the top down, you should get 49.25 plus 10h plus h squared minus the 122.5, which is 122.5 plus 49h plus 49.9h squared minus 122.5. So the 122.5s cancel out. You end up getting 49h plus 4.9h squared. I can factor out an h. That's important because when I can factor out the h, that means those h's can cancel out, and I have the limit as h goes to 0 of 49 plus 4.9h. So the answer is 49. Meters per second. So at 5 seconds, it is now traveling at 49 meters per second. Mm-hmm.
When you, for a question like this, when you get the limit, you get the answer, do you still need the right limit and please prove it?
No, that's your answer now. Yeah. Yep. So my function was 4.9 x squared, right? Okay. So 4.9 times x squared, or sorry, x plus h squared plus 4.9 x squared over h. So this time I just didn't plug a number. Okay. I didn't plug a number. Actually, you know what I'm going to do? Instead of using x, because I think that might confuse, I'm going to use the a. I just left it as a. So if I was to multiply out the top here, boil it all out and everything else, it's going to come out to be very similar to what we just had. It's going to come out to be 9.8 a plus 4.9 h. Don't worry, we're going to do one of these out in a minute so you can actually see all the process of what I just did. But I really wanted you to see, so this comes out to be 9.8a. What's 9.8? Well, speed of gravity. So as you're falling, gravity is pulling at you at 9.8 meters per second. It is accelerating you at 9.8 meters per second. That is changing your velocity by 9.8 meters per second. That's where that came from. So your position is the 4.9 t squared. Your velocity is 9.8 t, and your acceleration is just 9.8, which is the speed of gravity. Okay? We're going to look at these a lot more in a few minutes, and a lot more later on. You're going to use position, velocity, acceleration, and jerk actually quite often in a lot of these word problems. Okay, but that's where the speed of gravity comes from. All right. So, new little notation. Notice this part over here is exactly the same, did not change. However, the thing in front of it did. That little symbol right there stands for the first derivative. Okay. F prime. That's what it is, F prime. So F prime of A is the first derivative. You can also see it in all those other ways. They all mean the exact same thing. Calculus was invented by two people. Anybody know who they are? Newton is one of them. The other one starts with an L. Leibniz, Englishman and a Frenchman. Both actually invented during a pandemic. What'd you guys do in 2020? So yeah, it was like that was the joke in 2020. It was like Newton invented calculus during the pandemic. What'd you do? So because two different people created it almost at the exact same time, they use different notations. They each have their very use cases. So these are right here. Those are Newton's methods. So that's Newton. And these right here are Leibniz. Leibniz. And I totally spelled his name wrong. Hold on. I will get his proper spelling. Yeah. Yeah, that's about all I got right. Leibniz. Let's try this again. Leibniz. Leibniz. That's the proper spelling of his name. Oh, he was German, not French. Sorry. All right. So the last two you're not going to see very often. Those are more used in computer science. But the first groups you will see quite often. Okay. So you have f prime of x, you have y prime, you have dy over dx, so it's the derivative of y over the derivative of x, derivative of the function over the derivative of x. ddx is the derivative of the function of x, so those are the ways that you'll read it. Each one of those, like I said, has different use cases depending on what we're looking at, and you'll see those a variety of those use cases when you're going through Calc 1, Calc 2, Calc 3, differentials, and however far you need to go. All right. So let's find the derivative of this. So we're going to use this equation. So we're going to use the same equation as x goes, as h goes to 0. The only difference is instead of an a, we're using the x, which can make the first step more confusing because we're going to keep the x. So what I would typically do in these is instead of trying to just plug them all in, I would simplify down as much as possible. So what we're going to do first is we're going to find f of x plus h. We already know f of x. We've got that there. So I really just need to find f of x plus h. So that means that's x plus h to the third minus x plus h. All right. So now that is not x to the third plus h to the third. You have to FOIL. And you actually have to FOIL twice because it's x to the third. So you have x plus h times x plus h times x plus h. So you have to FOIL it out multiple times. So FOIL that out. We should get x to the third plus So we end up getting x to the third plus 3x squared h plus 3x squared h squared plus h to the third minus x minus h. That's f of x plus h. All right. Questions with that? Like, you can see where all the little mistakes that you're going to make is, yeah.
Go over. I want to say how to foil because
So how to FOIL, but not how to FOIL. Got it. No, I'm just kidding. It's fine. All right. So you have x plus h times x plus h. We'll start with that. You get x squared plus h plus 8. I'm sorry, plus hx plus hx plus h, right? So x squared plus 2hx plus h squared. Yes?
Oh, never mind, I got it.
And then we multiply that by, that's fine, I'm gonna finish now, I got one more step. So x to the third plus 2hx squared plus h squared x plus x squared h plus 2h squared x plus h to the third, which comes out to be 3hx squared plus 3h squared x plus h to the third. But as you can see, there's a lot of little places you can screw it up. You might have seen this at one point. Anybody remember what that is? That's Pascal's triangle. So Pascal's triangle, if you look at it, it's basically the sum of the things above it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 3 is 6. If you look at this one right here, and you look at my coefficients, they're the same. Pascal's triangle allows you to fill out binomials to basically infinity, and it'll tell you all the coefficients of them. You don't need to memorize it. It's fine. It's just one of those things that if you remembered Pascal's triangle at some point in the past, unfortunately, now with all the testing and everything else that we have to do in high schools and stuff like that, those fun little things, and it's, I know you're thinking like, how is that fun? It's fun to create it, and it's like it makes sense, and it's a pattern that people can create really easily. We used to do fun little things like that. Now you just don't have time to do those things anymore. So, but that's basically a binomial expansion. So you can expand it out forever that way. All right, so there's my FOIL. So we now have limit as h goes to 0 of x to the third minus 3x squared h minus, was it minus or plus? It was plus. Plus 3xh squared plus h to the third minus x minus h minus x to the third minus x. All over h. Okay. Because I don't feel like writing this a million times, you should notice that I have a negative x, those there, and the same thing there, correct? And I'm subtracting it. So those all cancel each other out. Yes, but I end up, it's, so it ends up being a minus, so it's x to the third, and then you distribute the negative sign, so you have minus x to the third, which ends up canceling it out. You have negative x here, this one's going to be a positive x, which again cancels itself out. Now you should notice that in every part you have left, we have an h. And we have an h on the bottom. Okay, so I can cancel out an h from everything. So I end up with 3x squared plus 3x h plus h squared minus 1. Which equals 3x squared minus 1. That is my final answer. That h, if you cancel it out, you still need to have a 1 there. Because the h's disappear because they go to 0. So remember, that's where that limit piece, so don't lose the limit piece, comes in. Basically, everything we're doing up to that point is trying to get rid of the h on the bottom because I can't divide by 0. Once I get rid of the h on the bottom or get something on the bottom that I can plug in h2, I plug in 0. And then all the h's vanish. So the only things left are the 3x squared and the -1, the two things that did not have an h. So the derivative of x to the third minus x is 3x squared minus 1. Now I can technically tell you any point on that graph, and you can find me the slope. Okay, that's nice. That's useful. So if I know the position of an object at any position, I can find the slope for it. Just plug the number into that one. So if I wanted to know the slope at 2, when x equals 2, I plug in 2 to the slope, the formula that I just did. So I plug in 2 to this, and I'd get 11. And that's my slope. Okay. All right. You're going to try this one. I'm going to write the problem down so you can see how it looks. And then you have to simplify it. Simplify. Also was a question on your test. Except there was a number in there, not an H. Yeah. But the F distance. What? You don't need the F. Why not? Because you're plugging in. You're not writing this side, you're writing this side. So if that was 3, you'd put a 3 there. You wouldn't put F square root of 3. You just put the square root of 3. So that minus F divided by H. Now I gotta simplify it. Yeah. I don't know if it's gonna help you. Yeah. What do we do when we have square roots? Start to the C. Where?
Oh, I know what we're doing. Oh, you see what's going on this.
Start with a C.
Right.
Yay. Good. How do you compare? Minus to a plus.
You just do it.
Just change the minus to a plus, multiply something up.
Oh, okay. It's fine.
Which minus?
The only minus in the problem, actually. There's only one minus in this problem.
We're not there yet.
Neither. I had a square root of h over h.
Square root of h over h.
So you multiply the entire bottom by the entire bottom.
Yeah. Whenever you're multiplying a fraction, you have to times the top and the bottom by the same thing.
I thought it was just multiplied by the right side.
No. Because you're basically getting the difference of squares so that they're going to cancel each other out. So it's the square root of x plus h squared minus the square root of x squared, which cancels out the square roots. Now the top, the x minus the x, is gone. So you end up with an h over h square root of x plus h plus square root of x. And now my x's cancel out. So this ends up being just 1 over 2 square root of x. Because if I plug in a 0 for h, I get square root of x plus the square root of x, which is 2 square root of x. Okay. So you can start to see how I think most people get the concept of plugging what this is and how to find it and why that's the case. It's all the algebra that you have to do to get down to the final answer. That's really causing you most of the trouble. Now you remember why your pre-calc teacher told you that this is the most important class you're going to take. Because it's all the mistakes you're going to make in calculus are not calculus. They're algebra. So it's just a lot of practice. Speaking of practice, have fun with this one. There is. I just didn't write it down yet. I will in a moment. All right. Common denominator. So multiplying the first one by 2 plus x. The second one by 2 plus x plus h. Boil it all out. And then the 2's cancel out, the x's cancel out, the negative 2x cancel out, the negative x squared cancels out, the negative hx cancels out. The only thing that's left is negative 2x h. So the only two things that do not cancel out is that and that, which gives you that. That's just the top. We then have to put that whole thing over h, which means now the h is on the top, cancels out. So that h will cancel with that h. And now I can plug in the 0. So I end up getting negative 3 over 2 plus x squared. Because this will become just 2 plus x, because the h goes to 0, and that's 2 plus x. So the progress that we're going to make, so your next test is until March 20th. Because over the next month, I'm going to teach you all the rules to do this so we don't have to do this formula out. Okay? But, so there's a good thing and a bad thing about that. No, you don't have to do this formula out. This formula will always work. It just sometimes is messy because of all the algebra in it, but it'll always work because this is the actual definition of a derivative. There's a lot of rules to make it work without using this. Okay, some are simple, some are complicated. Okay, so that's why for the next month, that's what we're going to be working on. Also, remember next Monday we don't have class. I was just thinking of that because next Monday is President's Day, so there's no class next Monday. So, all right. What here? So there are 3 situations where a derivative does not exist. So remember, we're working at a derivative is the limit, correct? As it goes to h, or as h goes to 0. And it's telling me the slope at those points. Okay. So if we look at these three situations, what does the slope look like it does there? What's the slope at that point? Okay, so the slope as it goes this direction is doing what? It's positive, right? It's going up, correct? So that's a positive slope. The slope over here are negatives, right? So at that point, for this to work, the slope would have to be 0, right? But that's going to a point, not 0. So as the slope gets closer and closer to this, it's becoming basically going to almost infinity. So that doesn't exist at that point. Therefore, I can't find the derivative at that point. Okay, so there are certain situations where I cannot find the derivative because the slope does not exist. A perfect example of this is the equation for absolute value. Okay, so if we're looking at the limit as h goes to 0 of this, so it's the absolute value of x plus h minus over x over h. If we're on the negative side, okay, so if x is less than 0, the absolute value of x is really negative x, correct? So as it goes to that, so I have negative x plus h minus x. Oh, sorry, minus negative x. So this becomes the negative x and the negative x cancels out. So I have negative h over h, which is negative 1, correct? Because I'm saying x is less than 0. So I'm looking at just the negative side, because absolute value can do both sides, right? So if I'm saying x is going to be negative, I'm giving you that information. I'm saying x is negative. So if x is negative, I know the absolute value of x has to be negative x. Because whatever value is in there is going to be negative. So negative and negative 3 is positive 3. Right? So I know that if my x is going to be less than 0, I know that the absolute value of x is going to be equal to negative x, whatever x happens to be. Okay? So basically, I'm looking at it coming from the negative, the left side. Now, if I look at the exact same thing, except I'm looking at it from the other side. So if x is greater than 0, that means the absolute value of x equals just x, right? So I have x plus h minus x over h, which ends up being just h over h, which equals 1. So the limit coming from one side is 1. The limit coming from the other side is negative 1. So does the limit exist at 0? No. because that's not coming to the exact same point. Remember, it has to come to the same point. So the absolute value is a perfect example of that corner. It comes to, if you look at the absolute value equation, it comes to that point, right? So that's what's happening there. It's going to two different values. Therefore, that limit does not exist. Same concept with the discontinuity. If there's a break in it, my limit coming to those points from two different directions to go to two different things, therefore my limit cannot exist at that point. So I can't find my slope at that point. And the last one is a vertical tangent. So a vertical line. Because your slope is going to what? Infinity. Huh? Yeah. Yeah. Right. The slope is undefined at it. Correct. So again, can't find my derivative at that point. All right. Here is those equations or those statements of what they mean. All right. So it's giving me the equation for the path of the projectile. It's 2 plus 24.5 t minus 4.9 t squared. You don't need to worry about its initial velocity because that's formulated into the actual equation. It wants us to find the velocity after 2 seconds, after 4 seconds. It wants us to find when the projectile reaches its maximum height, when does it hit the ground, and which velocity does it hit the ground. So it wants us to do a whole bunch of calculations. Instead of sitting there and doing each one individually, let's find the derivative of this equation first. Then we can just plug in 2 seconds and 4 seconds and other things and do it to find the answers. So find me my derivative using my limit equation of 2 plus 24.5 t minus 4.9 t squared. So we want to find our velocity equation, which is our first derivative. So right now you use, actually I'll rewrite it over here just so you see it. 2 plus 24 t minus 4.9 t squared, and you're going to use your limit as h goes to 0 of f of t plus h minus f of t over h. So you can use that equation. Okay. First of all, don't put the f in front if you've plugged good things into it. And in the other one where it says f of t, put the equation. Oh, actually, I take what I just said back. Never mind. You put the f where you put it. You were fine. You didn't actually plug in the equation, plug in the part yet. You're fine. This one should not be nearly as complicated as the last couple that we did. Actually, this was just a bunch of. No. That's. The whole. Yeah. Different. H. So yes, that's just f of t. I should have wrote that as f of t instead of h, because technically it's the height of the actual object. That's why they used h. But that's a, oh, you didn't do it. Okay. I was literally sitting there trying to find it in your paper. That's okay. It's fine. And then you have that oil. You cancel and clear things out. All those wonderful hundreds of steps that they're gonna make little signs and tape on. And then you go look at it and you're like, where did I go wrong? Something's wrong here.
I'm sending it up close.
Let me see.
I'm not like, I don't know, I'm like. That's what's supposed to be here. It's not T plus H.
No, you're replacing the t plus h where the t's are. So it's 2 plus 24.5 t plus h minus 4.9 t plus h squared. You replace the t with t plus h.
Oh,
You replace the T. with-
wait, so you leave the T there?
So this first step
Oh,
becomes 2 plus 24.5 t plus h. minus 4.9 b plus h squared.
And that's just for the first part. And then
That's
you do it
just
for P afterwards.
That one you already have. You just literally have to write that in. All right, if you go through and do all your wonderful steps out, you should get 24.5 minus 9.8. And the crazy thing is on Wednesday, I'm going to show you how to go from here to here in one step. All right. So how would we find the velocity at 2 seconds? Right. So another way to write this is also known as the velocity of t. So you'll also see that written as vt. Okay. So I would just literally plug 2 into that equation. I'd plug 4 into that equation to find the velocity after 4 seconds. So the next question comes up is, how do I find its maximum height? Okay, I can do that. I can just find the what of the original problem. The vertex, right? Okay. What's the slope at the vertex? It should be 0, right? So as you're getting closer and closer to the vertex, you're slowing down, correct? At the vertex, you should be going 0. So I could just solve this equation for 0. Now think about this for a second. What's b? 24.5, right? What's 2 times a? So it's b for negative 2a over 2a. It's right there. So let's look at the graph of this. So here's my graph. Okay. My vertex is at 2.5. The purple line is my derivative, my slope. At 2.5, my derivative is 0. My vertex, same point. Okay, so we can use the derivatives to find information about my original graph. Okay, at 0, you're going to have your peaks. Maybe not be the maximum depending on what the functions are, Okay, but it's going to change direction or something there. It's leveling off at that point. Before that point, before 2.5, what are the slope are what? What's all the values over here? They're all positive. And if we look at the graph, my graph is going up, which would mean a positive slope. After that point, my slopes are, I'm going down, right? So my slopes are negative. Look what happens after that 2.5. We're now in the negative areas. Okay. So it can help find that information. It cannot help us find where it's going to hit the ground because the slope doesn't tell me that. Okay. In a real life situation, when it hits the ground, it's obvious the slope would be 0. But when we're graphing it, it doesn't know that. The function can keep going. In reality, it's stopping. Okay. However, if I wanted to find the velocity when it hits the ground, I'm not looking at the velocity when it hits like on the ground. I'm looking at the velocity as it's going into it. Now think about it. If we're shooting off a missile and I want to know like velocity and mass when it hits, that's the amount of power or energy that's released. So the faster the velocity as it's going into the ground, the more damage it's going to cause. Okay. As horrible as this all sounds, the majority of this stuff was literally created because they had to figure out things for war. Even the original stuff back in Roman times when they were looking at trebuchets and catapults and stuff like that, they were looking at arcs and figuring out where things hit. They needed to figure out all that stuff. So this is where the mathematicians were getting paid by the governments at the time to do this stuff. Okay. And now we're using it to do a lot of other things, but that's the original use case for it. Okay. All right. We're done for the day.